Welcome to the fifth lecture of the fifth week of this course on machine learning. This lecture will be about case-based reasoning. Case-based reasoning, CBR, is the process of solving new problems based on the experiences from solutions of similar past problems. Expressed in an alternative fashion, CBR does solve a new problem by remembering previous similar problems and by reusing knowledge of successful problem solving for those old cases. Case-based reasoning can be motivated by assumptions such as similar problems normally have similar solutions, many domains are regular in the sense of successful problem-solving schemes are invariant over time. Case-based reasoning should be contrasted by rule-based reasoning. An interesting analogy here is always when you look at law systems. So there are some law systems in the world typically inspired by a German tradition, which are very, very much controlled by very strong rule systems, while the Anglo-Saxon legal system is typically case-based. So these are actually two camps in problem solving. Probably there is no simple answer that one is better than the other. They probably complete each other in some way. However, the focus today is on the case-based approach. So actually cases are stored, what we call in a case base or case memory, to be retrieved and used. When a successful solution to the new problem is found, the adaptive case can be stored in the case base to increase the competence of the system for future problem solving. So actually this functionality is what implements a learning behavior in this kind of system. Technically, case-based reasoning is primarily supported by the techniques described in the previous lecture on similarity-based learning or memory-based learning. Particular examples here are the schemes for distance and similarity measures, which is very important also to apply in case-based reasoning. So a crucial aspect of a CBR system is how the cases are represented. It's necessary to represent both the problem and its solution. And one can say that the representation problem here is even tougher than in the pretty simple conceptual learning cases we looked at earlier, because a case, including its solution, is a complex entity. So the representation needs engineering. So the representations of problem are the basis for case retrievals, and the representation of case solutions are the basis for case adaptation. So different forms of representation are the classical ones: feature value lists, graphs, predicate logic. As for all machine learning techniques, feature selection is a crucial sub-process here. The choice of representation is also crucial for which kind of similarity-based learning techniques can be applied and utilized. One common way of modeling a CBR system cycle of activity is the following. 4 main phases. Retrieval, where you try to find similar problems in the case base. Reuse the proposed solutions belonging to the similar problems. Revise those solutions so they fit and can solve the current problem. And then take the revised and adapted case and store it back into the case base again, which we call retain in this case. Actually, this goal can also be depicted a little more in detail. So we can see here we have a problem, we have a new case, we make a retrieval where we search among all the old cases. We select a few that has some close similarity. We try to reuse them on the solved case. That leads to some revisions and some repair, and then we make a modified copy of the case that really solves the problem at hand, and then we can store that problem again in the case base to be used for further problem solving in the future. So let's talk shortly now about each of these 4 phases if we now accept this model of case-based reasoning. So the first phase we call retrieve. The goal is to find a small number of cases from the case page with the highest similarity to the current case. So retrieval can be based on different kinds of technique. One can choose to have some kind of indexing techniques for everything in the base, and there are of course very different approaches to indexing. Also, you can focus more on the similarity learning techniques, instance-based learning techniques, and for example apply the nearest neighbor method using a weighted sum of features. Finally, there are also other approaches, something called template retrieval, where you return all cases that fit certain parameter settings. In the end, you typically return a very small set of closest cases for further processing. The next phase is called reuse. So reusing a retrieved solution can be very simple if the stored solution can be used and changed as the solution for the new problem. This is not the typical case though, so otherwise adaptation is required. The 2 main techniques for adaptation in CBR are, you can say, transformational, that actually takes the previous solution and modify that based on some domain-specific transformation operators. So it actually transforms the solution. The other approach, called derivational, where you reuse not the specific solution, but the algorithm, method, or rules that were used to generate the original solution. And then you apply them again in a different way to produce a new solution. So you need to create something different, but you can do it more in a, I would say the transformational is more a surface-oriented way, and derivational is more in a more deep sense. The third phase is called revise. So in this phase, feedback related to the solution constructed so far is obtained from the environment. This feedback can then be given in the form of correctness rating of a result or in the form of manually corrected revised case. So the retrieved case is adapted to reflect difference between the new case and the retrieved case. If the solution is unsuccessful, the retrieved case can be repaired by using domain-specific knowledge. After the solution has been successfully adapted to the target problem, the result can be stored as a new case in memory. The final phase is called retain. So retain phase is the learning phase of a CBR system in the sense that is where the revised case is added to the case base again. So depending on circumstances, a revised case can be either actually retained or simply forgotten. That's also a possibility. The new case is integrated in the memory structure either by indexing or by being positioned in the feature space, depending on if you have a indexing philosophy or more of a similarity space or instance space philosophy for how to structure the case base. It may also be that the case-based structure may be consolidated due to the addition of a new case, but by changing somehow the indexing mechanism or reconsidering the importance of features and so on. Actually, when we look back, we can say that if we talk about learning in this kind of system, there are two of the phases that are more relevant to talk about learning. On one hand, I would say it's relevant to talk about learning in the revise phase, because there actually you create something new based on the experience from the new case, and then more technically to integrate this new thing into the existing memory structure in the retain phase. So actually learning is more related to the two later phases, while problem solving are more related to the two first phases of the whole CBR cycle. It could be interesting to compare CBR to other reasoning and learning approaches. One key difference between the implicit generalizations in CBR and the explicit generalizations in mainstream inductive machine learning systems is concerned with when the generalizations are made. Most inductive algorithms make their explicit generalizations from a set of training examples before the presence of any target problem. We call this eager generalization. This is in contrast to CBR, which delays its typically implicit generalization until testing time. We call this lazy generalization. CBR therefore tends to be a good approach for rich, complex domains in which there are a multitude of ways to general a case, which is not trivial to handle in the mainstream inductive machine learning tradition. Let's look at some advantages with CBR systems. Cases are sometimes the best way to represent knowledge, especially when the available models of theories are unreliable, weak theory domains. A good case is often an efficient shortcut in the search for good solutions. The capability of a CBR is organically increased by the incremental addition of new cases. Intrinsic advantages of an old case can be strengthened by incremental improvements due to the adaptations triggered by new cases. The processes of storing cases and reading cases can be computationally less expensive than alternative learning mechanisms. Criticism of CBR is not uncommon, especially from advocates of much more strict formal methods. These critics of CBR argue that CBR is an approach that accepts anecdotal evidence as its main operating principle, so that without statistically relevant data for backing up the implicit generalizations, there is no guarantee that the generalizations are correct. As an example of a response to this criticism, recent research has defined CBR within a statistical framework that formalizes case-based inference as a specific type of probabilistic inference. So this is, of course, some kind of defense for the method, but still this debate goes on. CBR is a very much applied area. So not surprisingly, there are many very active application sectors in this case. So on this slide, a few of those are mentioned. The more important ones: help desk and customer service systems, recommender systems, not surprisingly, medical applications, in particular in diagnosis, applications in law, in particular in the Anglo-Saxon law systems, as I already commented on, technical troubleshooting, and financial management and decision making. Finally, I just want to give you a very small example how cases of this kind could look like. So here you find an example from technical troubleshooting. So you can see you have a few stored cases and you have a new case. And you have, of course, a number of features, as we have in machine learning in general. As been said here, what you need to do is you have to describe the problem in a domain specific and clever way, so that it's naturally easy to find similar objects in a constructive way. And then, of course, the next problem is how should you also represent the solution, which normally is even more tricky task to design the good representations for solutions, because the solutions, of course, should then, in a later stage of the process, be adapted. There is no time, unfortunately, in this part of the course to go any deeper, but if you are interested in CBR, please study the further reading that is recommended, and there you can get much more information about both applications and concrete cases like this. So this was the end of this lecture. Thanks for your attention. The next lecture, 5.6, will be on the topic of the tutorial on the assignments for this week. Thank you very much.